A system like Apollo, it's a great asset. To build a vehicle that can take 10 people to orbit and do some useful work as a vehicle, it's pretty hard to put a tractor rocket on the nose of that rascal and yank it free when something's getting ready to happen. It just doesn't work very well. We looked at all kinds of systems like that. It didn't work very well. So we said, we'll get the safety we need in this system by very careful attention to materials, loads, safety factors, single failure points, all the rationale, and in things like our guidance, navigation, and control system, we'll put just about all the redundancy you can think you'd ever need. Because the only time we ever used the escape tower in a Mercury program, it was an unmanned flight. The Atlas lifted off with the Mercury capsule on it, and the programmer didn't start. Fairly simple electronics, just like sometimes you turn your computer on, it didn't start. The programmer didn't start. So the vehicle flies straight up. It doesn't start the roll or the pitch program. Well, a range safety officer says, well, I've got no program. I'm going to have to destroy it. Let me know when you want me to destroy it. So we told him to wait till it gets up a little distance. He let it go up to about 14,000 feet. When the range safety destruct signal went in, the signal to send the tower lifting the capsule off, and it worked beautifully. It popped the capsule off, then the booster blew up. Capsule landed out in the surf. We picked it up and had it back in hangar S in about 15 minutes, and we flew it on the next mission. Escape towers work beautifully if you got a little package that you can do. But also you have to be careful when you put escape towers on there and you put an abort sensing system in there to tell that escape tower to take off, and you get a failure in that abort sensing system, you've taken off. So you introduce a bunch of potential problems while you're trying to solve some potential problems. Now, safety is getting a lot of discussion these days. Safety is not an absolute. For some reason, Newton never covered safety, so we don't know a formula for safety. Safety is a judgment factor on the part of the people doing the work. So we thought we'd put an electronic guidance, navigation, and control system on this vehicle that had all the redundancy you'd ever need. We weren't going to worry about a computer not starting, because if a computer didn't start, we had 3 more. So we put 4 computers in the thing, put 3 of this or 4 of that or 2 of that, worked all through it for quite a while, and had a GNC system that we thought was about as redundant and as foolproof as it could be. And I was talking to Chris one day, and I said, Chris, we may want to call Hewitt Phillips from Langley to come down and look at our GNC system. Chris had worked for Hewitt Phillips at Langley, and I'd written a couple of reports with Hewitt at Langley. And Hewitt was a good controls man. So Hewitt comes down and looks at this thing. We didn't have the 5th computer at that time. He looked at it, came back and said, well, Bob, I think it looks fine. The only thing is, if you have a basic problem of some type in your basic computer program, it's, you know, I don't know what's going to happen. And I said, well, what do you think, Hewitt? He says, all I would do is put a 5th computer in there and put a separate program in it. So we put a 5th computer, put a separate program in it. If the Ares 1 has this good a guidance system, then it might be as reliable as the Shuttle. I don't know. I have no idea what to have in Ares 1. I do read what the Ares 1 is going to be an order of magnitude safer than the Shuttle. Generally speaking, when an engineer comes in and tells you order of magnitude, he doesn't really know what he's doing, but he picked up that term somewhere in differential equations, and he learned order of magnitude's a nice term, so he tells you I'm going to be an order of magnitude better. You want to kind of watch that sometime. Let's go to the next chart. Thermal protection system. There were 2 big arguments back then. Let's go build a vehicle out of new hot metal structure. We're going to build some new materials, unobtainium type of materials, and we can make this thing out of materials that can handle these temperatures. And you thought, 3,000 degrees? Aluminum melts at 600. What the hell are you going to build it out of? Anyway, the people who argued to build a hot structure vehicle, I don't think ever had a very strong argument. But to build an aluminum vehicle and handle temperatures in some places of 3,000 degrees, other places cooler, does require pretty careful attention to the thermal protection system. You know how to go build the airplane, but now how are you going to protect it from getting too hot on entry? Well, fortunately, a fellow named Julian Allen had done some work at Ames years ago and had taught us that if we used a blunt body to re-enter the atmosphere and pushed a big shock in front of you, you could re-radiate most of the temperature back into the atmosphere. So you want to push a great big heavy bow shock in front of you, but you still get pretty hot behind it. We picked up on that in the Mercury program, picked up on that in the Gemini program, picked up on that in Apollo. It's still a good way to do it. So in bringing an airplane like this, we wanted to push a big shock wave in front of us. And then we wanted to cover that aluminum airplane with some material to keep it from getting too damn hot. We knew in places like the leading edge of the wing and the nose would have to go to some sort of ceramic material, something you had to heat way up to make it become a material. And then we hoped we could put on the rest of the hot part of the vehicle insulation that was light enough and a good enough insulator that you could meet the 19,000-pound weight target we had for the TPS. Fortunately, we had two companies, Lockheed and GE, working at that time. And the silica material that Lockheed was working on turned out to have the insulation properties we needed. It's kind of fragile. You handle it too much, it's kind of like styrofoam, it breaks and so forth, but we were then going to glue it on the aluminum with a strain isolator plate. And we had the TPS, as you see there, pretty well in mind, but we'd never done it before. And we did a lot of testing. I remember one day we were running some tests out on the West Coast, out at Ames. And it was in a blowdown tunnel that heated the air with a copper heating element. And that heating element failed for some reason, and it put a lot of copper particles in the airstream that hit the TPS, the silica tile TPS, and eroded a good deal of that tile off as the heat pulse hit that test specimen. And someone brought it in and says, we had a failed test. And I said, well, what did the back face temperature be on the aluminum? Oh, it got up to 225 or 30 degrees, well above where it was supposed to, but well within what would survive. So I said, that wasn't a bad test. You can knock a lot of that silica tile off on the vehicle. It's very, very forgiving in one entry. And I'm sure we spend a hell of a lot of time keeping it all looking good and keeping it all filled up good. But I think we tend to be a little bit too nervous about the silica tile. But it's pretty clear to us right now, if you hit anywhere on that carbon-carbon with 10 to 20,000 foot-pounds of energy, you're going to knock a hole in it. Now, I don't know whether it's possible to come behind the TPS and put a ablative fence in the wing or something that would make the wing more heat resistant. I don't know whether they're even working those kinds of things on Shuttle these days. But the Shuttle has worked pretty well with the thermal protection system. It costs us more than we'd like. It's a worry. But to bring an aluminum airplane back from Earth orbit and absorb the heat energy you have to absorb, that's where we are today. And then the straight wing versus the delta wing argument, in my opinion, was an argument that was taken way out of context. For this kind of application, the double delta wing is obviously, in my judgment, the right thing to do. You don't even want a wing on the thing while you launch it. And you'd like to get the thing flying as soon as you can when you come in. You'd like to have as much maneuver volume as you can for aborts and for landing in Edwards or landing at New Mexico or landing at the Cape. A delta wing, we learned in earlier days as we first began to go supersonic, is a good structural configuration. It's a good configuration to have trailing edge flap type controls on. So we went to the double delta wing for lots of good reasons, in my judgment. We worried a little bit of whether we had enough L over D to make it a reasonable landing vehicle. We did not want to go all the way to a lifting body. That's getting a little bit too low. We had some experience with lifting bodies out at Edwards, and they're marginal. We put enough wing on this to make it a pretty good flying machine. It does not meet the kind of standards you'd like for landing and handling qualities on a commercial airplane, but when you can position a thing at what we call the hitting alignment circle, if you can position it up there, get it lined up, let it do its natural thing down to the runway, it flies very nicely. It also doesn't respond a hell of a lot to little gusts and that sort of thing. It's such a poor aerodynamic thing, it doesn't respond to it. It just flies down very nicely. Now, once we took the vehicle to this configuration, as I told some of the people earlier, we once looked at having air-breathing engines to give us a go-around capability in landing, or to ferry it across the country, because you know, you land in Texas, you'd like to get back to Florida. So it's a 250,000-pound pain in the neck once it gets on a runway to get it back to the thing. So, but we wanted to get rid of the air-breathing engines. Owen and John Kiker came in one day and said, after we decided we'd get rid of the engines, we were struggling with, now what do? We go strap a bunch of engines on it and put the tanks in the payload bay, or could we tow it? It's such a lousy aerodynamic vehicle, you don't want to think about towing it. And Owen and John came in one day and said, why don't we put it on the back of an airplane, fly it? Well, hey, that's probably a pretty good answer. And I told you about GAO trying to figure out how to account for taking the engines off and going to 747, and I think we finally convinced them that's a wash. They didn't have to worry about that. But anyway, the 747 thing worked very effectively. One of his people modified the well, let me tell you the 747 story. Shortly after we'd gone to the 747, we were worrying about how to put it in our budget. And someone came in and saw that there was an American Airlines used 747 on sale for $18 million. And this was in the middle of a budget cycle. So I called George Lowe and I said, George, can you find us $18 million? He found $18 million, and we bought the first airplane. Of course, Owen wasted $29 million putting all those tails on it and making it fly, because he was worried about the CN Delta. It didn't quite have enough CN Delta with that orbiter up there straightening the airflow over the tail, so we put some vertical surfaces out. Could I have the next chart, please? In any event, let me go on now to another part of the program and I'm just picking a few things in the program to tell you the kind of thinking and what we were doing. Once we began to look at this stubby configuration, putting the orbiter down where we had it so we could use its engines and recover its engines, we knew immediately we had a vehicle that had a whole lot of very low frequency natural modes of vibration. We had a natural pogo generator. Those of you know what pogo is. It's a coupling between the structural movement and the propulsion system. So what are we going to do? Well, in Owen's office, he had a bunch of technical people we had 10 key technical managers. And we decided that under the structural key technical manager, we would set up a pogo prevention panel. We didn't want a pogo panel. We weren't looking for pogo. We wanted to prevent pogo. So we set up a pogo prevention panel. And that pogo prevention panel, we found people in industry, people in academia, wherever we could, and we put together the best pogo prevention panel we could find. And then every time we came to a spot in the program where we could get some data to feed into that pogo prevention activity, whether it was a full-scale test, whether it was a model test, whether it was a component test, we took the data and fed that data into the pogo prevention panel. We were pretty well pogo-free except for one concern between the two pumps on the engines. It looked like there might be a chance for those two pumps to couple in such a way to cause a problem. So we put an accumulator between those two pumps. Cost us 700 pounds, each engine. I hope they still got those accumulators in there. In any event, that's the way in which we worked the program. We did not do a probabilistic risk assessment. We could never convince ourselves it was worth the effort, because we kept coming to a situation where we thought garbage in, garbage out. You take a bunch of factors that are not statistically honest and then begin to maneuver those factors around arithmetically and come out the other end with a series of nines. If you're not careful, you're just kidding yourself. So we did a lot of single failure point analysis. We did a lot of sneak circuit analysis. I signed off on a hell of a lot of things that the safety people brought me. But that's the way we went about dealing with structural dynamics. Again, to give you a feel for how you can't put two women on the job, and Owen, you can correct me on this, from the time we had a wind tunnel test of the configuration until we'd gone through all of the aerodynamic analysis, all the structural analysis, all the vibrational analysis, we used to call it the MMLS, model, modes, loads, and stresses. A MMLS cycle, as I recall, took us about 18 months. And had we put twice as many people on it, we could not have done it in 9 months, I'll guarantee you. We'd put twice as many people on it, it's probably taken us 24 months. Okay, let's go see what we got next. Anyway, here's what the vehicle is. I thought maybe we had people in the audience that didn't understand the shuttle, and I'm sure you do, but let me do a little of this. I bump into some people occasionally and say, what the hell does the shuttle do? All it does is go around in circles. It doesn't go anywhere. They don't seem to appreciate the Hubble telescope, the fact we took it up there with the shuttle, put it in place. In fact, we went back up there and corrected the optics. The fact that we've gone back 3 or 4 times, it's probably the greatest telescope man's ever operated. Now, should Shuttle get credit for the Hubble? Of course not. But did the Shuttle allow us to have something like a Hubble? I think it did. This thing has 2 cockpits, if you will. It has a cockpit they use in launch and landing. Then there's another cockpit behind that they use in working on orbit. It also has a docking interface. It has an airlock. It used to take 65,000 pounds to 28.5-degree orbit at 100 nautical miles. I don't know what it does today, but it does pretty good payload to and from orbit. It's frankly the vehicle that has given this country an ability to have, I think, a very viable manned spaceflight program for the last 30 years. And I think we ought to be very careful before we throw it on the scrap pile. Let me expand that a little bit. As we were developing this shuttle, you put together what are called operations and maintenance requirements documents, OMRSDs. Now, if you don't know what that is, that's a document that tells the people in the launch site what they have to do to operate this vehicle and maintain it. There are hundreds of these documents. And these documents today now are 30 years old. They're mature. I'm sure they're much, much better than they were in the first set of OMRSDs we sent to Cape. Those documents alone have cost the taxpayer of this country one hell of a lot of money. And it'll take a long time before you have another set of OMRSDs as good as the ones you got today. I can say the same thing about the software in this system. The man-hours and the money that's spent in the software development lab to make sure there are no glitches in the software in the GNC system are very, very large, and they're very time-consuming. And you can't put twice the people on the job and do it in half the time. As I said earlier, we named it poorly. It should have been called the Low Earth Orbit Transportation and Work Vehicle. It does not go to the moon, but it could take some vehicles to Earth orbit that could then fly to other places in the space or universe, whatever you want to call it. And I'm happy to begin to see that maybe out of this Augustine committee, we're beginning to think maybe there's a way to go about exploring space without just building an Apollo on steroids and brute forcing ourselves back to the surface of the moon again. Particularly now, this time, we got to do it with an Earth orbital rendezvous and a lunar orbital rendezvous. And we got to do it with stuff that's going to take a hell of a long time to develop. But anyway, I'm off my subject. Let's go ahead. Next chart, please. This is a familiar thing to you. Go ahead to the next chart. That's a familiar thing to you. Go ahead to the next chart. Those are familiar things to you. Go ahead to the next chart. That's a familiar thing to you. Let me just comment here. I spent the first, let's see, 8 years in the space business picking capsules out of the ocean. And you can do it. We had a couple, we nearly drowned a chimpanzee one time, and we nearly drowned Gus Grissom one time. But other than that, it went pretty smoothly out there. It is not a particularly good post-landing environment. And the Navy was very cooperative and very helpful, and it can be done. But it's not nearly as elegant as landing like this and getting out of the damn vehicle. So I think we also need to be completely comfortable we're going back to capsule technology. Next chart, please. I've already talked about this. Next chart. You can see the tails Owen put on it there. Next chart, please. I had to figure some way to get off the stage, and I'm getting off with this chart. There's a lot of concern in the country today about the fact that it's been X years since we first landed on the moon, and here we don't have a research station on the moon, and we're not progressing. And quite often I hear Lewis and Clark. Lewis and Clark went up to the Northwest, and boy, in 20 or 30 years, the settlers were running through the Missouri River and up across the Rockies and grabbing up land in the Northeast. And why aren't we doing that on the moon? I'd like to call your attention to Antarctica. Antarctica is a continent, as you well know, here on the Earth. It has good air, plenty of air to breathe down there. It's very moderate temperatures compared to the moon. It's a little bit cooler than Houston, but it's not bad. Someone told me one time there's a lot of cold down there, but hell, there's still a lot of cold in West Virginia. But in any event, if you go back and look at the history of what we have done in Antarctica, we as a people, we've got an agreement now where no country can claim Antarctica. Well, we've got that on the moon. But there's still some countries that go down to Antarctica, and you can, as a tourist, go to Antarctica today. But do you know how long it's been since the first man landed on Antarctica? Look at that chart and figure it out. I think it's nearly 200 years. Now, I don't know where we'll be in going to the moon 200 years from now. If we've got a Walmart there, that's great. I think we need to be a little more patient. And if we're going to insist that the authorization and presidential groups recommend big increases, and that the appropriations people will give those big increases before we continue manned spaceflight, I think we want to think about it carefully before we lay down the gauntlet. Because if we're asked to live for the next 15 or 20 years at 0.5 something % of the budget, it might be a good idea to figure out how to do it. And I hate to see us not keep Shuttle and space station on a fairly healthy path. Because we talked a lot of foreign people into helping us on the space station, and a lot of them thought we were going to be operating the shuttle to give them a ride up, give them a ride back, bring everyone what they wanted back. And we ought to think about it before we pull a plug on all that. Gary, I think I've used most of my time. Now, since this was a lecture, he said we were going to have plenty of time for questions. And I told him if I didn't get any questions from the audience, could I ask the audience questions? And he said yes. So if you don't ask me any questions, I might ask you one. So let me open it up. I got a question. Let me make sure I can hear you, because Dot's been fussing at me so much I finally had to go to some hearing aids.
You kind of skipped over a decision I thought that was a very gutsy call during the development of Shuttle, and that was taking off the air-breathing engines. And I often wonder, could NASA make a decision like that today? NASA seems so risk-averse. I'm interested in how much risk you saw in making that decision.
Well, I touched on that briefly, but let me get more depth in it so you fully understand. When we went to the configuration that you now know as the Shuttle, about all the propellant you could afford to take to orbit was enough to give you one go-around capability. So in the later part of the landing, you had to know you were in some trouble, start some engines and get them thrusting to help you out, and then you had enough to go around one time. Otherwise, you begin to use all the payload. The old rocket equation gets you. You know, you get awfully big on the ground for every pound you take to orbit. So we began to look at that. We said, why would we ever miss a landing and have to go around? Well, you miss it because you're not positioned right up here, or you don't manage your energy right. Well, we said, gee, if we aren't right up here, the chances are we're going to be very unright. It's going to be way out somewhere. So the chances of being at the hack, if the GNC system's working and you understand the forces and you've got reaction control systems to give you force when you don't have aerodynamic force and so forth, we were pretty well convinced we could hit the hack. We were pretty well convinced that we got into the hack and we managed ourselves down the glide slope, we could get it on the runway. And at that time, they had developed some microwave landing systems that when you put on the runway, gave you very accurate information as to where you were on the glide slope. So we put those systems on the landing fields, microwave landing system on the field, and we just convinced ourselves it was a safe operation, particularly for the L/D we put in this vehicle, because we felt we could manage it. Now, we looked a lot at landing criteria. If you look at the landing criteria that the University Research Group up in New England, the name escapes me right now, they have a certain criteria for landing. The Shuttle was not high in that criteria, it was down in the middle, but it landed pretty well. When we did the first ALT test, if you look at the movies on Fred Hayes' flight, he got into a PIO pretty well before we got on the runway. We looked at what the problem was there, and we found two problems. One, Fred had made a bet he would put it down on the numbers, so he was trying to make the airplane sit down on the numbers. We also had a logic in the flight control system to where, and it's a rate command system, if you needed some pitch rate and at the same time needed some roll rate, it gave you the pitch rate you asked for before it gave you any roll rate, which was a bad logic in the flight control system. And we also had the gains a little bit too high. So we went in and we didn't even do another test. We went in and degained it a little bit, changed the logic between the roll and the pitch axis. We put people in the vertical simulator out at Ames and made dozens of landings. And we just convinced ourselves that we didn't have to have the go-around engines. It saved us some weight, saved us some dollars, simplified the system, and as far as I can see, the Shuttle lands there nicely. Was it a gutsy decision? Yeah, there were lots of gutsy. While we're on those kinds of decisions, let me ask you a question. I'm going to ask the audience questions. How many of you think the Lindbergh system could pass the Aerospace Safety Advisory Panel's meeting? And I met with the Aerospace Safety Advisory Panel once a month. Wouldn't do it. The government would not allow Lindbergh to fly the Atlantic. He had a gas tank in front of his windshield, so he couldn't see out front to land properly. He only had one engine. That's no good. He was one pilot, and you know damn well one pilot can't work for 33 hours. His navigation was pretty crude. He didn't have a wind compensation system. I can give you 100 reasons why Lindbergh shouldn't have flown. Now, I don't mean that we should build a shuttle on taxpayers' money and ignore good safety considerations. And safety is a part